Hello and welcome to the FlexSim Core training course. My name is Cliff King and I'll be your instructor. Chapter 1, an introduction to simulation. What is simulation? Well, one popular definition out there is the imitation of a system based on knowledge or assumptions about the behavior of the parts of that system with the purpose of obtaining insight in the behavior of the whole system. What is a simulation model? Well, in general terms, it's a purposeful abstraction of a real-life system which can be used to answer questions or solve problems. It contains only those elements of reality that are needed to answer the question or solve the problem. Discrete event simulation, also known as DES, is used to model systems which change state at discrete points in time as a result of specific events occurring. Some examples of system events might be parts arriving, product movement, machine process start or finish times, machine breakdowns, and repairs. Examples of states for machines might be idle, processing, down. Q states might include empty or full. Operator states, off shift, utilized, idle. And transport states would be things like traveling, loading, or unloading. Simulation modeling can usually be broken down into these three parts: queuing, processing, and movement. Simulation modeling is all about managing time, the time spent doing something, waiting for something, or going somewhere. Queuing occurs naturally whenever entities arrive faster than they can be processed. Processing in modeling is simply a forced time delay on the entity being processed. Movement is the physical movement of an entity from one location to another. It's important to know the difference between inputs and outputs when modeling. Modeling inputs might be things like arrival rates, the number of resources, or processing times. Whereas model outputs are things like throughput, utilization of staff or machines, and states. Chapter 2, FlexSim Concepts and Terminology. When beginning a modeling project, some questions to ask yourself and others are: why build a model at all? What insight are you trying to gain? What problem are you trying to solve with this model? What is the central actor in your model? And can they or should they be categorized into types? What kind of arrival patterns do they exhibit? Where do they go and how long are they there in the model? What limited resources need to be available to them, like machines, tools, or staff? To what degree does physical layout affect model behavior? Things like sizes, distances, planned routes, are they important? When starting a new model, you need to ask yourself, how do you measure time and distance in your model? Is it going to be seconds for time, or minutes, or hours? What are your time units going to be? What are your length units going to be? The default units of time and distance are seconds and meters respectively. Units are set per model, and once they are chosen, they cannot be changed for that model. The defaults for future models are defined in global preferences if you want some defaults other than seconds or meters. The model clock during a simulation will display in either elapsed number of units or as the model's date and clock time. Alright, let's talk about FlexSim's 3D object library. A library is a list of class objects to be used in building a 3D model. It's user customizable or expandable for specific modeling needs. Here is a screenshot on the right here of the objects in the 3D object library. It's categorized into fixed resources, task executors, travel networks, conveyors, and so forth. An instance is a copy of one of the library objects. It's created in the model when an object is dragged from the library icon grid into a model view window. 3D objects are reusable, pre-configured components. They're speedy, simple, easy to use in model building, and highly visual. They are customized with menu options or code writing. It's a decentralized logical organization. Every object, in other words, is its own independent actor. It simply receives an item and then does something with it. Usually holds on to it for a certain amount of time if it's a processor, and then sends it on. I'm going to switch over to FlexSim and build a simple model for you now to help you better understand some of these concepts. This will be a simple model that will begin with a source. Source of parts that will arrive, enter a queue, proceed to a processor and be processed, and then exit the model into a sink. Okay, after creating these objects in my 3D model view, I now want to connect them up. Otherwise, nothing happens when I run the model. Reset, run, clock moves, but nothing happens. Okay, reset the model. To connect objects together, you can use the menu button up here to switch over to the connect mode, like that. You can see by the cursor change that we're in a connect object mode. There's also this disconnect objects mode, which looks like a broken chain, and this takes you back to the standard mode. But I want to teach you the shortcut for entering connect mode. It's the A key on your keyboard. So if I hold A key down, it changes the cursor. I'm keeping the A key held down, and then I click and drag between the source and the queue, then from the queue to the processor, then from the processor to the sink, and release the A key and return to normal mode. Now if I hit the reset button and then start running the model, you can see parts moving through the system. It's kind of fast. Let me slow it down. The flow items are represented by this box icon by default, but of course that can be changed, as well as the 3D graphics associated with any of these objects in the model. Well, why does the model work when I haven't defined anything? Well, let me stop the model and show you. There's some defaults. So the source, if I click on it and look over here on the right in quick properties, there's this field called enter arrival time, and it has something there already. It's an exponential distribution with a location parameter of 0 and a scale parameter of 10, and the random number stream is taken from the current object itself. And in this little view window, we can see a histogram of 1,000 actual samples that use that distribution, just so we can get a better feel for what it looks like on a frequency chart here. And we see that the mean is about 10, which matches the scale, and the standard deviation is 10.2. So parts are arriving about every 10 seconds. And then at the processor, it's got a setup time of 0 and a process time of 10. So it's processing them every 10 seconds. Arriving about every 10 and processing 10, but because we're using an exponential distribution for the inter-arrival time, it's not exactly 10 seconds between each arriving part, and therefore you can see the queue rise and fall. Let me speed it up. You see the queue going up and down. Okay. The processor has an input port receiving items from the queue, and then if you look over here at another important parameter called the send to port field, you can see it's choosing one of its output ports. In this case, it only has one output port with a option called first available. That's a quick introduction to modeling in the software. So let's stop, reset the model, and switch back to our PowerPoint presentation. Okay, all of the 3D objects in the 3D object library have events behind the scenes that are going on. If we look at the events associated with the processor object, it'll hopefully give you a better understanding of how events and objects relate. So, what happens, we'll start up at the top left, when a flow item enters a processor object? Well, an on-entry trigger fires. It can be found on the Triggers tab of the properties for that processor object. Then a setup time field fires to determine what, if any, the setup time will be. Is an operator needed for the setup time, yes or no? If yes, it makes a call to the operator and waits for the operator to arrive. And then it goes into a delay, forced delay, representing the setup time. Then there's a trigger that occurs at the end of the setup time called the onSetupFinish trigger. Then we move into the process time. Well, the process time field needs to fire to evaluate how long the process time will be for this particular item that just entered. And then, is an operator needed or not? Then we delay for the process time and possibly have to wait for an operator if an operator is needed. At the end of the process time, there's an onProcessFinish trigger that fires. Now it's time to evaluate where the flow item needs to go next, and this is done in that field called Send to Port. It fires, returns a port number to determine which of the output ports of this processor object will a flow item be sent to. There's a possible delay at this point because we need to wait for the downstream object that was chosen to be available, and if it's not available, we will wait for it to become available. Then the question is asked, is a transport needed to carry the item or take the item from this processor object to the downstream object that's connected to the chosen port in the Send to Port field? Well, if a transporter is required, then we might end up having to wait for that transporter till it arrives over here and picks up the item. And then the item, when it gets picked up, or if it just naturally leaves because no transport was needed, an on-exit trigger fires, and then the flow item has left. So what is an object? Well, it's a collection of events or activities packaged together in such a way that it can be easily applied in a wide range of simulation needs. Has a limited sphere of influence, and it works wonderfully as long as you aren't trying to make it do something it wasn't designed to do. Okay, here's some object modeling principles. We have flow items, they cause the events. We have objects that define system behavior. It typically represents a physical location or resource that needs to be interacted with by flow items and or other objects, especially task executor objects. And then you have port connections. This is how you manage object acquire and releases. Provides a means for inter-object communication and coordination. Objects are broken into different classifications. The two main players are fixed resources and task executors. Fixed resources are objects which send and or receive the flow items. And task executors are mobile resources that perform assigned tasks. We just saw in the sample model I built, an assigned task was to come pick up the flow item and carry it to the sink, or whatever the next object is. Object properties. Object properties can be edited either through the quick properties for some of the more commonly used fields, or you double click on the object in the 3D view and it'll open up a new panel as shown here with all the properties of that object organized into tabs like the processor tab, breakdowns tab, flow tab, triggers, labels, and general. Object port connections. Well, there's two basic kinds of connections: output to input port connections and center port connections. Output to input port connections define possible flow item routes to or from the fixed resources. So if we look at this queue in this screen capture of a 3D model view, where a conveyor is sending items to the queue, and then the queue has got connections downstream to one of two processors. You can see that this arrow here is pointing towards the queue. That's an input port. These two arrows are output ports ordered numerically from top to bottom. This is the first output port, and then it has a second output port connected to each of the two processors. Now this square port down here is called the center port, and they're showing a connection from the center port of the queue to the center port of an operator. Now center ports are for referencing purposes, and they're often used to point to a task executor like this operator here to be called for the processing of the item or transporting of the flow item. Port connection modes I pointed out when I built the little sample model. It can be accessed through the toolbar. If I had clicked on the arrow next to that A connect symbol, I would have seen three options to either connect objects or connect center ports or extended connect. And then the associated keyboard shortcut is shown next to it. So connecting objects is done with the shortcut key A on the keyboard, S for center ports, and D for extended connect, which we haven't talked about yet. And then there's the same three for the disconnect modes. If you want to exit a mode, you can hit the escape key on your keyboard or right click your mouse button. So this little diagram organizes the 6 keyboard shortcuts to help you maybe better remember them. And if you look at your keyboard, you can see that's where they're organized on it. The particular letters don't mean anything. They're just a convenient place on the keyboard. So we have, if you're making a output to input port connection, it's the A like we talked about. To connect, it's Q for disconnecting. Or if you just want to view them, use the V key. Center to center, W to disconnect, S to connect, and C to view. You can reorder the ports on the General tab for the object, because port order may influence the behavior slightly. For choice of downstream object, for instance, you might want to reorder those. The one connected to output port 1 gets a preference over port 2 and port 3, everything else being equal. Okay, the output or push flow options are as follows. On the flow tab, there will be a send to port field, defaults first available. There are several options to choose from, or write your own code if you want. So the send to port field defines a rule for sending flow items to downstream objects via the ports of this object. The use transport box, you check it if you want to use a transport to take the flow items to the port designated by the send to port field. And this reference to which transport to use is done in this field here. And the default option there is to choose the transport that is connected up to the current object center port 1. Okay, chapter 3. We're going to talk about building models in FlexSim using the 3D object library. I'll go over some model building strategies, and then we'll jump right into our first model, modeling exercise 1, which will be built in 5 phases. When you first begin a new model, gather all the available information that describes the system, from how it looks to how it behaves. Take an incremental approach to the design and implementation of the model. Think layers. Build your model up in layers, just like we're going to do in this first model. If you want to break up model building into steps, here's 5 basic steps. First, create a 3D layout. Include a CAD drawing if you have one. Build a flow chart of the process to use as a guide during the modeling process. Define the logic for each step. Test as you go. Run the model and view the results. Okay, let's go over the description of our first model. Model 1, Phase 1. What's the purpose? To gain familiarity with object-based modeling principles. Here's the description. Every 120 seconds, a flow item is created that represents a packed shipment of parts. Each shipment is composed of 4 parts. Each part is processed individually for 10 seconds per part. An operator is responsible for placing the parts onto the conveyor and setting up the machine. The setup time is 3 seconds. The operator is not required during the 10-second processing time, but when the process completes, the operator needs to carry the flow item over to the sink in the model. And then we'll look at outputs. What is the content history of the parts waiting to be processed? What is the throughput of processed parts? Here is a layout of the model. There's 6 objects in this model. The first one on the left is the source. It generates your flow items, passes them through a port to the separator. This is a new object I'll discuss on the next slide, which will separate it into 4 individual parts, place them in the queue. Then the operator, this person right here, will carry the flow items from the queue over to the machine and set up the machine. The machine will then process the parts. When the processing time is finished, the operator needs to pick up the part and carry it over to this object called the sink. Okay, let's talk about the separator object. It behaves like a processor with the added ability to separate a flow item using one of 2 options, unpack or split. Unpack assumes the entering flow item contains additional flow items within itself, and then the contained flow items will be taken out or unpacked. The split option for separating receives a flow item and releases a given number of cloned flow items, and this includes the original. So then you have the split/unpack quantity field. This quantity field takes an expression value and either unpacks that number from the container or produces that number of copied flow items. And the count value you put in the split quantity field should include the originals. So we'll be putting the number 4 there because we want 4 things to leave. Okay, now let's talk about simple output dashboards. All objects in your model keep track of basic statistics about themselves, such as throughput, content, and stay time. All of these are accessible in chart form from the Object Statistics property window. If you'll open the panel in the Properties window called Statistics, as shown here in this slide, there will be thumbtacks next to each of the statistics associated with throughput, content, and stay time. If you click on the thumbtack, it'll ask you how you want to display that stat, as a time plot or as a bar chart. So it's very easy for you to create some dashboards for this model. Okay, it's now time for you to try to build this model on your own. Okay, I'll now go through the model building process for Model 1 Phase 1. So first, drag a source out, then the separator, then a queue, then a processor, then the sink for the terminating point where our flow items will leave the model. Okay, now a operator. If I click here, I can have a choice of different operators to choose from. If I choose the custom one, that's kind of nice because then I can click on it and modify things about it. I can choose as a starting point one of these shapes, and then change skin texture, different heads associated with them, and then clothing, even accessories like glasses and gloves. Okay, next I will right click to get out of object create mode, Hold down my A key on my keyboard to go into connection mode, and then click, drag, connections, like so. The connections I will make with the operator are center port connections for referencing purposes. So that's the S key. Hold it down. Click from the queue to the operator because I want the operator to be called to the queue to pick up parts to carry to the processor. And I also want to use the operator to do the setup time at the processor. So hold S down and click and drag a center port connection from the processor. Okay, let's click on the source. I can use the quick properties on the right or double click to open up the full properties window. And we were told that every 120 seconds a flow item is created. So we'll use the enter arrival time. We're not going to use a distribution. So I'll just type in 120. Our model units are in seconds. I've used the default model units of seconds and meters. So 120 represents 120 seconds in between flow item arrivals. This actually represents a shipment that's composed of 4 parts. So hit OK to exit that properties window. Double click on the separator. And we want to remove the process time for this. Has a default of 10 seconds. We don't need a process time on this object. Its sole purpose is to create a total of 4 items. Let me go to the separator tab. Not going to use the unpack option. That's for when you're taking flow items out of a flow item, and our flow items that are arriving are just standard flow items at this point. So I will split and define my split quantity as 4. Now 4 includes the one that came in. Get that one and 3 copies. Click OK. Go to the queue. Double click. Max content by default is 1,000. That should be sufficient. On the flow tab, I will check this box in the output section under the send to port field to use a transporter to take the flow item from this object to the next object. And the way it is being referenced by default is the object that is connected to the current object center port number 1. If you ever need to reselect that option because you've typed something else in and want to go back, rather than type current.center objects bracket 1 bracket, you could just choose this option here. And then it gives you the opportunity to specify which center port. This object only has 1 center port. Click OK, we're done. Go to the processor, double click it. Has a max content of 1. We were told to process each of the 4 parts one at a time for 10 seconds with a 3-second setup time. So setup time 3 seconds. Process time's already at 10. These times are per item that enters. We want to use an operator for the setup time, not for the process time. If we did, we'd check this box here. And then we need to have the operator carry the flow item to the next object. Well, that's on the flow tab under the send to port field. Use transport, and we're set up for the center port already. Hit OK. Go up to the reset button, click it first. Over to the run button, click it. And let's check our model. Hit step to jump to the first event. So first flow item entered and immediately went through the separator, turned into 4 parts. Separator had 0 time on it. The operator is carrying a box over, putting it on the processing machine. Setup time's finished, then the part starts processing. These parts are conveying across the top of the processor, according to their process time. That is an option on the processor. It's this box here, which is checked by default to convey items across the processor lane. And it conveys them across, indicating how far into the process time it is. You'll notice when the flow item first enters the processor, it goes to the middle of the box, and that the time it is there is the 3 seconds for the setup time. Then it jumps to this left side and starts conveying across. That's just animation. I like to leave that on. It's a good debugging tool. We can tell how far into our process time we are based on how far across the surface of the conveyor or whatever object it is. Okay, everything appears to be working there. Let me stop the model, reset it. Now we wanted to find out the content history of the parts waiting to be processed. So those parts are waiting here on the queue. So to get a dashboard, it's as simple as clicking on this object, the queue, where the parts are waiting. Go over to the Quick Properties pane on the right. Open the Statistics panel. And see, these are standard statistics that are automatically collected on this object. So let's look at content history. That's this thumbtack here. Click it. Pin to a new dashboard. We don't have any dashboards created yet. If we did, it would have the option to pin to whichever dashboard already is created or pin to a new dashboard. We can look at content or content versus time. It wants a content history, so let's choose the content versus time option. Opens up a dashboard and puts this time chart widget already in it. We can resize it. Ready to go there. We can look at the model run, but before we do, let's create the other dashboard chart, which will tell us what the throughput of processed parts are. Good place to do that is either on the sync or on this processor. Let's click on the sync here and choose this throughput tag here. Pin it to our current dashboard and then choose what we want to display, either throughput or output versus time or input versus time. Let's choose the one that just says throughput. It's going to give us a little table showing our sync and both the input and the output, but a sync only has input. Alright, let's go over, reset the model, start running it, and speed it up. We can see our stats being collected and displayed in our dashboard. Looks like the content of the queue never really rises above 4, so we're able to keep up, which is what we would expect with enter arrivals every 120 seconds and only 10 seconds per piece, plus a 3-second setup and some walking thrown in there, but altogether no queue. Now, we purposely did not have any stochastic distributions in this model yet, but we will do that next. So let's spend a little bit of time talking about these statistical distributions. First of all, these distributions, what are they used for? Well, they're a way of capturing the real-life variance. In real life, you do not have an exact time of 120 seconds in between each shipment arrival. It's going to vary. You don't process each part for exactly 10 seconds. That's going to have variance associated with it. Well, we need a way of mathematically modeling the variance in these times. So on this slide here, I've got an example of 4 different statistical distributions displayed in what we call a density function plot. Now, the x-axis on these 4 plots represents the value that the distribution is being used to model. Maybe it's a process time or a setup time or time between arrivals. That's the x value axis. The y-axis is a relative probability. Don't need to get hung up in what the values mean exactly. I'm more interested in you getting a feel or an understanding for how to read these charts in terms of their shape. Of course, when you go up on the y-axis, you are increasing in probability. The frequency of occurrence goes up. This top left chart here is a curve associated with what's called the normal distribution. Many of you have probably heard of this distribution. It's also known as a bell curve. This normal distribution density function plot is symmetrical about the mean. So the mean is right about here at 0.7 or so on the x value axis, and then it falls off in probability symmetrically to the left and to the right. The probability of values higher or lower than that mean value is less than the probability of the mean value itself. Whereas a function like this one on the bottom left here, called the log normal distribution, has a curve that is asymmetrical. The mean value is probably, just looking at it, looking at area under the curve, is maybe somewhere in here between 1 and 1.5. Whereas the highest probable value to be returned, as noted by this peak here, is something like 0.5, 0.6. And the probability of some really large values being returned is possible, but the probability is low. This top right one's an exponential distribution. It approaches zero, never hits it on the left, and theoretically goes out to infinity, and the mean value is somewhere in here. And this distribution here is a Weibull. These distributions have parameters, and based on the parameters you assign to the distribution, the shapes will change slightly in some of their cases. Okay, so these statistical distributions randomly generate values. Keep in mind they generate those values per the frequencies defined by the probability density function of the distribution. What you need to know to use them is the name of the distribution, the parameters it requires, and where to use it. So let's talk about that. Now, as far as which distribution should be assigned to which variable in your model, we provide a tool called ExpertFit that can be used to find a distribution that matches your real data. Feed it real data and it crunches on it, does some curve fitting algorithms, and spits back the different distributions that it found that could possibly match your data, and then you choose one of them and use it in the software to model the variable of process time or whatever the data is associated with. Here's some examples. The last parameter of every statistical distribution in the software is the random stream value. 1, 2, 3, 4, up to however many streams, and we have an infinite number of streams you can use. And typically modelers will just leave that as is, leave the function called getStreamOfCurrent in there, and then it will assign a random stream uniquely to each of the objects in your model. Distributions that return real values typically have to do with time, like the random interval of time between flow item creation, or the random duration for a process or a setup time. Whereas distributions that return integers are commonly used for things like choosing a random object port in your model. Let's click on this processor object and then come over here, and in the process time field where it has the 10 seconds we were using, I'm going to click the down arrow here, look at the list of choices, and one of these options is statistical distribution. When I hover over that, I get a list of all the different distributions in the software. There's many of them. Let's look at this one called log normal mean and standard deviation, because you're going to be using that one. This is nice because it clearly identifies what the parameters of the distribution are. This first parameter is the mean value. The next parameter is standard deviation, and this is the stream. It shows you a histogram spread of 1,000 actual samples generated from this distribution at the time you open the window or change a value. So if I put in a new value here and say 33 for the mean, and the standard deviation 12, then it generates 1,000 samples. The mean comes out exactly 33. The standard deviation from 1,000 samples is something close to 12, but because it's only 1,000 samples instead of an infinite number of samples, it's not exactly 12. Let's look at another distribution. How about the gamma distribution? This one has a location value, a scale value, a shape value. Right now, with a scale of 5 and a shape of 2, the mean is coming out to be 10.24 and a standard deviation of 7.22. Let's see how the shape value affects the histogram. Oh, look at that. It starts making the hump of the curve move to the right. Let's see, how about a 5 in there? Even more so. How about a 12? Start sending it more and more to the right. Scale value, drop it down to 2. How's that affect the curve? It affects the mean value, but the shape of the curve is staying the same. And location just shifts everything over. If we say 20 here, see how the x-axis starts at 30 now? So this is a good place to get a feel for the different distributions. So now I want you to build phase 2 of Model 1. The purpose is to introduce randomness to the model, as well as an introduction to labels for custom outputs. We're going to use a label in order to get a chart, a dashboard chart that shows us throughput by rework status. Yes, that's the other thing we're going to do in this model. We're going to have some parts require rework, and you'll see in the description. So let's go through each bullet of the description. The arrival rate of our shipments, rather than being exactly 120 seconds, is actually going to be described by the exponential distribution now, with a location value of 0 and a scale value of 120. Those are the parameters of the exponential distribution. Still a mean of 120, that's what the scale value is, scale parameter is of an exponential, it's the mean, but the time between arrivals will vary for each shipment. The number of parts in a shipment, instead of being exactly 4, as it was in phase 1, it's going to now be described by a distribution called D uniform, D for discrete, uniform distribution, with a minimum of 2 and a maximum of 6. So it's got a range, equal probability across that range. The setup times described by the triangular distribution, and the 3 parameters you need for that is a minimum of 1.5, a maximum of 4.5, and a most common, or otherwise known as the mode value, of 2.5 seconds. The process time is described using the log normal distribution. Because there's more than one type of log normal distribution, in the drop-down list, look for the one called mean standard deviation, one we looked at just a minute ago. And the mean value is 10 and the standard deviation is 3. Okay, there is now a 20% chance that parts will need to be reworked after processing. What that means is you need to route 20% of the flow items back into the queue and have them go through the process again. So in the send to port field for the processor, you'll use one of the pick list options for that field that can send randomly based on a percentage to one of its output ports. Not that hard to do, just look for the right pick option there and you'll be fine. Now as far as getting the throughput by rework status plot, we're going to want to label our flow items. That's going to be done with an exit trigger on the processor. So as parts leave the processor, I want you to create a label on them. And there is a set label option there you'll see. And you can label them with a label, let's call it rework. And then the value assigned to it will be whatever port they leave through. If you have a hard time with that one, hold off until I show you how to build this model. But give it a try first. See if you can figure it out. Okay, here's the layout for the model. It's exactly the same, but what you can see in this screen capture is that the processor has 2 output ports. The first output port is connected to the sink, just like it was in phase 1. Now you're going to need to create a second port coming out of the processor and route it right back into the queue. And then as far as handling the decision for which output port to send to, use the send to port field on that processor. Okay, now I'll demonstrate the completion of phase 2. First of all, let's edit the inter-arrival time for the source. I'm going to double click to open the full properties window for the source. Choose statistical distribution and look for the exponential option that we were told to use. Location 0, scale 120. Next, the number of items in each shipment is defined on the separator. The quantity will be a distribution. The D uniform. A minimum of 2 and a maximum of 6. The setup time is next. That is defined on the processor. The setup time field, choose statistical distribution and look for the triangular option. The minimum is 1.5 seconds. The maximum is 4.5 seconds. And the mode is 2.5 seconds. The processing time is also a distribution. For this one we want to use log normal. This last option, log normal mean standard deviation. The mean value will be 10. Standard deviation will be 3. Now, to handle the rework, let's first make our second port connection. So we hold A key down on our keyboard, click on the processor, drag to the queue and release. Now, there is a 20% chance parts will need to be reworked after processing and be sent back to the queue. Let's go back into the processor and go to the Flow tab. We want to use the option in the Send to Port field that allows us to send to a port based on a % probability. So that's in the random category, and it says by percentage. Then we can add as many choices as we need. We only have the 2. The first port that's already hooked to the sink, that's going to be 100 minus 20, so that's 80%, go to port 1, and 20% go to port 2, which are the reworks. Okay, the model will run at this point, but in order to get our dashboard chart that displays throughput by rework, we need to add a trigger. So let's go to the tab on this processor called Triggers and add a trigger. And the trigger we want to use is the on-exit trigger. And let's look at our options here. In data, we can set a label. Let's try that one. Going to set a label on the flow item. The label will just go with the default name of type. That's good enough. And then as far as the value, which we don't want to use what's there now, well, look at this. We've got an option to assign the outgoing port number as the value of the type label. So that's all we want to do here. Hit OK. Save our model. Mod 1 phase 2. Reset and run. Let's see if it's working. Okay, it's kind of hard to know if we're really getting rework. Let's look at our queue though. That's going up and down. Remember, we never had a queue more than 4 pieces before. Now of course we're making a different quantity, 2 to 6, but notice over time that queue just continues to rise. So we have an unstable system that really can't keep up. Let me stop, reset the model, and let's add a dashboard chart. So let's click on the dashboard, and we've got, last time we created our dashboards by just clicking on a thumbtack. Let's see if we can do that first. So click on this processor, go up to the statistics panel, and look at throughput, click the TAC, pin it to our current dashboard. Let's see if we have throughput, and then look at its parameters by double clicking on it. Can we change anything about it that would allow us to categorize by our label? There's nothing here, so this isn't going to work. Let me delete that. This time we're going to click on our dashboard and look at our different options in the library for charts. We can look at a throughput chart. How about this one? Throughput by type. Let's drag it over here. What object do we want to look at the throughput of? We can use our eyedropper. Choose processor 1. And the label that is going to distinguish the types is the default here is what we want to use, because that's what we called our label, was type. And its value is a numeric type and display type and throughput. Okay, let's see if that'll give us what we want. Reset. Run the model. And look at that. Throughput by type. This chart above it is throughput total. 566 is total. Down here we've got of type 1, which are good parts, 567. Rework parts is 143. The rework parts are sent back around and get counted twice, and eventually will leave through port 1. So port 1 is going to be the same as this one. It's off by 1 just based on when we stop the model. And then of those 567 that have been processed and left our model, 143 of them needed to be sent back for rework. Okay, this concludes Model 1 Phase 2. Okay, let's talk about labels. FlexSim doesn't assume any attributes of things represented in the system, so it's up to us as modelers to assign those attributes we need to track data or make decisions based on that data. For example, how much something might weigh could be a label. What is the SKU of the item? Was this part reworked or not? And we used a label for that in the last phase of the model. So, what is a label? It's a mechanism for storing information on just about anything. For example, objects, flow items, tokens. And there's 3 things you need to know when using labels. First is the owner of the label, where it is found. The second thing we need to know is the name of the label. This is determined by you and should describe what the label does to be a good name. And there are some naming best practices that we'll talk about. Next is the label value, the actual information you want to store on the label. This can be numeric, it can be a textual string, it can be a pointer. There's a number of different types of values. But in summary, you need to know the owner, the name of the label, and the value of the label. Okay, let's switch over and demonstrate where to find these labels in the software. So here's the model we just finished building. Let's get it running so we have some flow items in it. Okay, there's our first arrival. First part gets processed, and okay, good. It's a rework part. So let me click on that item that's being carried back to the queue that left through port 2 of this processor. And if we look over here in Quick Properties, we can see a list of all the labels that have been defined on that flow item. It has a label called type. So the owner is the flow item, the name of the label is type, and the value is 2, number 2. That was the port number. We can go and double click on the processor to remind ourselves where we set that label. That was on a trigger of the processor. Created an on exit trigger. We used the set label option, and if we look at the parameters for that set label trigger, it has the object or the owner is the item that exited the processor. The name of the label is type, and the value is a port value, either 1 or 2, depending on which port it left through. Okay, this processor also has a list of labels and quick properties. I should have left that window open. Let me go back into the overall properties, all the properties, and there's a labels tab dedicated to the list of labels. There are no labels on this. To add a label, you would click add and then choose what type of label you want it to be. A number label, for instance. Then you get to, and you just created that label on the processor. So the processor is the owner. This is the name of the label. Maybe you want to label this as produced. The number of items it has produced. And this is the value. And you could use a trigger on exit of this processor to increment the number of items produced by this processor, as an example. Lots of uses for labels, and we'll become very familiar with them by the end of the course. I'm going to delete that label definition. Okay, let's continue with our training slides and talk about label values. On this slide, there is a properties window of the labels tab of a flow item called box. The owner of the label will be this object, box in other words, and it's the object in charge of the label information. The labels reside on that object. The green section here show the names of the labels. So in this example, there are 4 labels on this box flow item. One called type, one called serial number, one called my operator, and one called SKUs. It's good to give a name to the label that indicates the job it has, but that's up to you as a modeler. The red section shows the values of those labels. This is the information that's stored on the label. It's used to make decisions, gather statistics, and otherwise affect model execution. The most common label values are numbers, text, and references to model objects. Like this first one here, the type label on this box flow item has the value 5. It's a numeric value. The serial number, on the other hand, is textual, and this particular box has a serial number of XYZ-123. The next label, called my operator, probably being used to keep track of the operator that processes this box, either should process it in an upcoming event or has processed it and has been recorded here for reporting purposes. It's a pointer type label. I can tell by the purple text, and it says /operator1. It's right justified. It's a reference to an actual object in the model called operator1. This SKUs label is an example of an array. In this example, the array has 3 indexes, and we see the 3 values of each of those array indexes. Assigning a label. Typically you won't just type in the value of a label in that last screen we were looking at, but instead you'll use modeling triggers to assign a label value when the particular event takes place. For example, the on exit of a processor. Over here on this image on the right, on the triggers tab, we see that a trigger has been added, a specific trigger called on exit. This trigger fires whenever a flow item exits the processor, and the set label pick option has been chosen, and the parameters are item for the object parameter, which is the owner of the label. The name of the label is type, and the value being assigned to that label is an actual distribution with a minimum of 1 and a maximum of 3. But the key point is the label value is being assigned in a trigger during runtime of the model. Okay, dashboard template library. When you create a dashboard, you can drag many different types of charts and graphs into that dashboard window. There will be a library on the left pane of the software showing you all the different types of charts and graphs that you can create. You can also create additional ones custom made by you, but there are so many to start with. During this course, we will typically just use one of the chart templates that are available to you. Charts are organized by the type: WIP for work in process, throughput templates, datetime templates, state templates, zone templates, milestone templates, etc. We saw how we could use labels in phase 2 of the model to create categories for statistic charts. Like we used the label type, remember, to categorize our graph according to those items, getting the throughput of those items that had been reworked versus the number that did not need rework. We're now going to move into phase 3 of Model 1. The purpose of this phase of the model is to learn how to use global tables to store model data. This is called parameterizing your model. We'll learn how to use triggers and labels to customize the model behavior. Here's the description. The parts that arrive via our shipments have one of 4 possible part number values assigned to them as a label. This table here contains the data on the probability of each part number. So here we have 28% probability we'll have a part number 1, 13% probability part number 2, and so on. And it contains the unique processing time parameters to be used for each part type. Instead of a 10 and a 3 for the mean and standard deviation that we used previously in phase 2 of the model within a log normal mean standard dev distribution, you're now going to need to look up a different mean and standard deviation for each part depending on its part number, as shown here in the table. The outputs we're looking for are what are the processing statistics, the min, max, and average, for the parts by part number. Okay, now let's look at some of the things you're going to need to learn in order to build this phase of the model. We'll begin with a closer look at triggers. When key events occur on an object, a trigger is fired. There are triggers like an on-entry trigger, which fires when a part enters an object. There is an on-exit. There is a process finish trigger. Lots of different triggers. They're unique by object type. So each object type has a unique set of triggers. The triggers can be defined on the Trigger tab of the Properties window. You may choose multiple options that are to happen when a trigger fires. So each trigger can have multiple pieces of trigger logic that do different things. Here is the trigger field. It's going to look like this. It'll have a name, like on entry, the field, and then a plus sign. This button here you click on to add a trigger option. This button you click on to delete a trigger option. After having chosen a trigger option, you would click this button here if you want to edit the code directly. And you would click this button here, the final red X to the right, to delete the entire trigger field. Now, after having added a trigger option to a trigger field with the plus button, the plus button will now look like this. It'll turn into an edit button to click to edit the trigger option. Basic object referencing. For now, you just need to learn about the variable name current and item. Current is the owner of the event. It refers to the object that you're writing the trigger code on or defining a trigger option for. The item is the flow item that triggered the event. So if we're talking about an on-entry trigger, the variable name item would refer to that flow item that caused this event to trigger on the object. We also need to know about referencing objects via a port number. References to connected objects are stored as an array for the object that owns those connections. accessible with the dot operation. So this is what the format looks like. You'll have the object itself with the connectors, the port connections, and then you say dot, and then what type of connection it is, whether it's a center object or an out object or an in object, and then brackets, and the number or an expression that returns a number will be the port number. So we've seen this before in our flow tab in the use transport field. For instance, we had current dot center objects bracket 1 bracket. That was there by default. We just took advantage of it and connected our center port from our object up to our operator. It's a way of referencing the operator we wanted to use for transport. So here's the 3 different things you might use to reference another object via a port of the current object. So you say current, that's the variable referring to this object that you're writing the expression on. Dot center objects for center ports, and then bracket the port number. Or out objects to refer to an object connected to an output port. This would be a downstream object, and an upstream object that's connected to this current object's input ports would look like this. And this is just showing you here that instead of a specific port number, you can use an expression that returns a number. And this is using the discrete uniform distribution that would return a number between 1 and 5, an integer between 1 and 5, a discrete number. Okay, global tables. They are used for all kinds of things. You can use them for referencing the data that will be used by the model during runtime, or you can have the global tables store or record data that's generated during a model run. So here's what it looks like. To create a global table, you first need to open the toolbox on the left. You'll see library there, and you'll see toolbox by default, or shown in the left pane. Click the add a tool, is what this means. Click the add button. You'll see this list. Choose global table, and it'll immediately open a table. And then using quick properties in the right pane, you can name that table. You can give it a certain number of rows and columns. We're going to want to do this in our model. We'll make a table with 4 rows and 4 columns as shown here. You can also import the data from Excel into one of these tables, or vice versa. You can export data that's found in a global table or generated there during runtime, for instance, and then export it out to Excel, to a sheet in Excel. Okay, let's talk about the different data types that the data within a global table can contain. The table cell data types are used to determine the format the data in the cell will be stored in. And this is important to know because the table methods will return different things based on the data type. So what are the different data types you can assign to the cells of a table? Well, we have numbers, which are integers or doubles, strings, text like names, words, or sentences, pointers, these are references to other nodes or objects, and the text turns purple. Arrays, these are ordered series of data with multiple elements. If you look down at this table below, you can see I have an example of each of the data types here. So showing 4 rows, and the column 1 here called number shows numeric data types, doubles and integers, a string column with names in it, pointer, this is the purple text. So what you see here are actual objects that are contained in this model. This is a direct pointer reference to it. And these are examples of arrays. Arrays can contain numeric data or string data. And the next data type is called FlexScript. The text you enter into a FlexScript data type cell will be treated as executable code. So it does need to be a valid expression. We also have bundles. They are data tables that store numbers and strings, rows and columns. And then we have track variables. Track variables will record a history of values. These are typically used for statistical histories. These data types are going to be set by first selecting, highlighting the desired rows and columns in the table, and then right-clicking, as shown here in this image. In this case, just one cell has been selected, but you could select more than one. Right-click on it, go down to Assign Data, and you'll see the different types of data types you can assign. Okay, global table access. If you want to look up a value from a global table for a process time, for instance, you'll be in the process time field, as this example here shows. If you click this arrow here, you'll get a list of options. One will be called by global table lookup. If you choose that option, then another little interface will show where you can specify the name of the table and then a reference to the row number in that table you want to use. And in this example, it's using a label on the flow item called part number. So the dot syntax is being used here, item dot name of label part number, and it'll use whatever the value of the part number label is for the flow item to reference the row number. The column, you can either define it with a numeric number or the title or header of that column. So process times table, we're assuming here in this example, has a column named time. So you can use column names or column numbers. The expression syntax will look like this. Use the word table with a capital T, and then in parentheses you would put the name of the table in quotes, and then bracket, a row number, close bracket, an open bracket, column number, and close the bracket. Okay, we need to talk about the empirical distribution, or in this case the de-empirical, discrete, D for discrete, empirical distribution. It returns a random sample from a discrete empirical distribution. You're going to need to use this in this phase of the model. The parameters are as follows. The first parameter can be a string, node, or number, and it's a reference to the global table containing the empirical data. And then the random number stream that you've seen already. And we leave it as it shows here most of the times, where it is a command called getStream, which will just come up with a stream on its own based on the current object. The table must contain a list of values and probability percentages associated with each of the values. The probability percentages, this is important, the probability percentages must be entered in column 1, starting with row 1 of the table, and their associated values are entered in column 2. The table may have as many rows as needed to define as many values as desired. The percentages that are entered as numbers between 0 and 100 in the first column, they need to add up to a total of 100%. Okay, now let me switch over to the actual software and demonstrate some of these concepts we've covered in these last slides. Let me begin by demonstrating how to create a global table in your model. Switch over to the Toolbox tab on the left pane. Click the Add a Tool button. You get a list of tools you can add to your model, and I'll choose Global Table. In the toolbox now we have a folder of global tables where it has created our first global table, and it named it Global Table 1 by default. It opened a view of the table here, and then in the pane on the right in Quick Properties we can change the name of that table if we want. Call it My Table. Give it the number of rows and columns you want. If you want to change the name of a column, double click on the column name and rename it. Let's just, as a demonstration, I'll assume that this first column contains the process times of 2 part types in our model, and on each row of this table we're going to define the process time. So part type 1 takes 4.8 5 time units, and this one takes 3.2 time units. Now let me go to my model, view, and click on Library tab, create another processor, and assume we want to define the process time on this processor according to what's in our table. So we choose by global table lookup, and we can choose my table from the list of global tables in the model. The row has an expression in the field already, item.type. This would assume that your flow items have a label on them called type. That's how you reference a label value. Just say item for flow item dot and then the name of the label. So if the type label on the flow item had a value of 2, it would look up its value out of row 2 in column 1. And you can either use column numbers or you can type in the name of that column. You're allowed to do that as well. Okay, it's now time for you to try to build this model on your own. Okay, I will now demonstrate the Model 1 Phase 3 changes. First of all, let's go to the toolbox and add a global table. Let's rename the table in Quick Properties on the right. We'll name it Phase 3 Part Nums. Let's give the table 4 rows and 4 columns. Then you need to fill out this table. I already have the information in a clipboard, so I'm just going to paste it to save time. Okay, there's our information. Now let's go over to the model view and create an exit trigger on the separator, and we'll use that trigger to set a label on each flow item as it leaves the separator. So double click on the separator, click on the Triggers tab, and add a trigger. There's a list of all the triggers that are available for a separator. We're going to use on exit trigger, and let's click this add button and see which one of these we want to use to set a label. In the data section, there's a set label. There's a set label and color. Let's use this option. Now we're going to set the label by percentage, but we're going to look up that percent value out of a table. So I don't want to use this one. I'm going to use this option, and then we're going to use the de-empirical distribution to reference the Phase 3 part nums table. You'll see that here. So it's going to set a label on the flow item, and the name of the label, let's go with part number. It's a good idea to use capital letters in the naming of your label and don't use spaces, and that's the convention that works best. Okay, for the value, it's a distribution, so I can use this pick option here and then choose de-empirical. Let me expand this so we can read the whole thing. So de-empirical is the function or command. First parameter is a reference to the table, either the string, node, or number. We'll use the string option. Double click in there and type the name of our table. Phase 3 part nums, and then the random number stream. Okay, that's gonna do it. And the reason that works is because we referenced a table where column 1 was a percent and column 2 was a value to return. These numbers here, 28, 13, 32, and 27, must add up to 100. And then it will return the corresponding value that percent of the time. And it's going to assign it to our part number label. Okay, that's what that's for. Get our label assigned on each part. Then, in the process time field for the processor, we're going to reference that table to get this mean value and this standard deviation value. Let me click here to edit it in this mode. It's a log normal mean standard deviation is the distribution type. For the mean value, we're going to get a value out of the table based on the part number. So it's going to look like this. We'll use the table class designator, and then in parentheses, we're going to reference our phase 3 part nums table. And then we're going to use brackets, square brackets for the row number, and then square brackets again for the column number. For the row number, we're going to use an expression. We're going to use the value of the label called part number of the flow item. That's easily written by just saying item dot part number. Okay, and then open up some more brackets here, and we can reference the mean value column, which was the third column, so I can either write a 3 in here, or to make it more readable, and if the format of the table was to change, this is the better way to go, type the name of the column, which is mean. Now it's pretty much that same expression for the standard deviations. Let me copy what I wrote there for the mean and paste it here for the standard deviation, and just need to change this to the name of that standard deviation column. Get all your capitals right and everything. Okay, let me check and make sure. Yep, mean standard dev. Okay. Alright, that's the process time. Okay, the next thing we want to do is create a dashboard. So click here in the dashboard, open the library, and we wanted to look at stay time. So stay time by type. Let's use this one here. I'm going to get stay time by the part number label. Let me write that in the title. Okay, need to be showing the model, so I can use the eyedropper to choose the entrance object and exit object. In this case, it'll be the same object. We want to know the state time within the processor. So click here, click on that processor. And for the exit object, same. Now the type label is, need to update this to say what the name of our label is, which is part number. Value type is a number. Display it as part, use a space here, number. Okay, and display all the stats, average, min, and max. Okay, let's run the model. Reset, run. Okay, let's pause the model right here. Click on these flow items, click on this blue box. Look at what label's been assigned to it. It's got a part number label, and it's a value of 3. What about the green box? Let's click on it. It has a part number label value 2. If we look at our table, we can expect for part number 2 a little longer process time, on average anyways. Okay, let's keep running. Look, that blue box needed rework. Let's go click on it, and we should see that a type label, remember that was the name of the label we assigned on the exit of the processor. When they leave, we write down what port they left through. So this value 2 was a rework part. Let's keep running. Okay, here's the green box being processed for a longer time, it looks like, and it's a good part. Let me stop the model there and click on it. It's part number 2. It now has a label called type with a value 1. Port 1 is hooked up to the sync and is for parts that do not need reworking. Okay, so it looks like our model's working, and we've got 2 values written in here so far. The average state time, which is only one part, so this was the state time of that first part number 2. That had a part number 2 was 19.61 minutes, and the green one, other way around. The green one that just finished processing is 19.61, and the blue one, which is part number 3, had a state time of 9.48. Okay, that should complete our update to the model. Let's save it as Model 1, Phase 3. And continue on. Okay, moving right along. This is Model 1, Phase 4. In this model, we'll learn how to use the combiner object, and we'll further use labels to aid logical decision making. The description. After the existing process in the model, the individual parts are going to be sent into a queue based on their part number. So for example, all part number 1 flow items will accumulate in a dedicated queue object for part number 1s. And then so there'll be 4 queues dedicated to each of the 4 part numbers. Then these individual parts need to be assembled at a combiner object with these following quantities: 4 of part number 1, 2 of part number 2, 3 of part number 3, and 5 of part number 4. And the output we're going to look at is how long does it take to assemble the components. This is what the layout's going to look like. So after our process, we're going to dump everything into a queue, a common queue, and then we'll make a decision based on part number to route it to either this queue, or this queue, or this queue, or this queue. Then this is the combiner object. Now you'll see there's an extra source here hooked to the first input port of the combiner, and that'll make sense in a minute when I explain how combiners work. But for now, just know we need another source here, and it's going to provide a pallet that will enter the assembly station here, the combiner, and then parts according to the quantities we looked at in the table will be drawn from these 4 queues and put on the pallet. And then we're going to be introduced to a conveyor. This is just a simple straight conveyor, and the pallet will convey down the length of the conveyor and then go to the sink. Label access expressions. So the syntax we've actually had to use already. You have the label owner and then a dot and then the label name. It's as simple as that. The dot operation is used to access the information stored in a label. So for example here, in the send to port field of our common queue, we need to do something like this: item dot part number, the name of our label. And remember, we have a label called part number on all of our parts. If it's a part type 1, then this will return a 1, right? Which means it'll be sent to port number 1. If it's got a 2 for its part number label value, it'll go to port 2. So it's direct port reference based on part number. That's pretty easy. It's not always the flow item that has a label. It could be the current object that has a label, in which case you would just say current dot item failure rate if that's the name of your label. This last example is showing you why it's a good idea to not put spaces in the names of your labels. If you do, then you have to use this syntax, like item dot labels, bracket, and then quotes, the name of your label, close quote, close bracket, dot value. Got to call the value method on it to return the value of a label called stocking space number. Whereas if you didn't use a space, then we can simply say item dot stocking number. So my guess is you're not going to put spaces in your label names. Okay, this is the combiner object. It can be used to do three things: either pack something, join something, or batch. When packing, this object will place the flow items into a special container flow item like a pallet. When you're joining, the received flow items become a single assembled unit. So for things come in, they get smashed, if you will, or joined together into one unit leaving. Now, the item that will leave is actually the item that came in through port 1, and it just has nothing changed to it. The other items that were combined just get destroyed, and that first part moves on. Batching, it collects all the flow items, delays for a process time, and then releases all the flow items individually. It doesn't pack or join them. Component rows are added automatically for each input port connection made for ports 2 and higher. What are component rows? Well, if you look at the combiner tab on the properties for the combiner, you'll see this is where you choose what you want to do, either pack, join, or batch. If you're going to pack, you get this components list here. This table gets populated with as many rows as the object has port numbers greater than 1. So in the image here, you see the first port number, it's green right here, meaning it's open, but port 1 is where it receives the container through, and then the components are considered those objects connected to ports 2 and higher, so 2, 3, 4, and 5 in this example. And you list the quantity of parts you want to receive from each of those. Input port number 1 is always reserved for the container or main part. The assumed target quantity for input port 1 is 1. You just receive one container in, like a pallet, and then it waits for the other components to come in through the other input ports, and after all have been collected, the process time starts, finishes, and the pallet or whatever flow item came in through port 1 will have the other flow items contained inside of it. They're not destroyed, they're put inside of it, packed inside. Okay, it's now time for you to try to build this model on your own. I'll now demonstrate how to complete phase 4 of Model 1. Let's add the new objects. Let me slide the view over a little bit. Slide this sink to the right. Pay attention to the port connection of the sink. It's output port 1 on the processor that it's connected to. We're going to break that connection now. Hold the Q key down. Click and drag. Add a queue. We'll name it non-reworks. Add 4 more queues for each of the part types. We're going to break them out according to part type. So let's call this part num1 queue. Part num2 queue. Part num3 queue. Part num4 queue. Okay, let's slide these together so it doesn't take up as much room here. Okay, need a combiner. Call this the assembly. We need a source, another source. Place it right here. It'll create the first part to enter the assembly or combiner object through port 1, and that becomes the container. That will be a palette we're going to create. So double click on this source. Let's use in arrival time, but 0 time between arrivals, and choose palette for what to create. Okay, let's make some connections. Hold down A key, click and drag to here. Let me change this port order before I forget. Double click on the combiner, the processor, and on the Generals tab, choose what type of port it is, and here we can change the rank of it. And now see how it went up to the first port number? That's what we want, because we have routing decision on this processor that says if you need rework, go out port 2, otherwise go out port 1. We need a conveyor, so use a straight conveyor section. Just click and click again. Okay, finish my port connections. A, click drag to each of these queues, 4 queues it'll be sent to based on part type. And then let's make sure we connect this source first to the combiner object, and then the others in order of their part number. Click and drag to the conveyor, and from the conveyor to the sink. Okay, now we just need to edit a couple objects. First, we want to edit this queue here. Double click on it, go to the flow tab, and we want to define a send to port expression that will send part number 1s to port 1, part number 2s to port 2, part number 3s to port 3, and part number 4s to port 4. Well, we can do that by using an expression in this field and saying item dot name of label, which is part number. We're going to use the value of the part number label to define the port number to send the item to. That's what that means. Okay. Now let's edit the assembly object, this combiner. Go to the combiner tab, and we'll define the quantities that we want to pull from each of the ports 2 through 5. So the target quantity for each of those is going to be 4, 2, 3, and 5, right? That's what the description told us. Oops, 4, 2, 3, 5. Okay, and the last thing we want to do is create a dashboard chart for the state time of the assembly object. So in the latest version, the dashboards have changed a little bit. The organization of them is all. So we want to use state time. If you see this little icon right here, it means you can click and get a sidebar here of the different styles of charts for state time. I'm going to use this table. Click here, and then all I need to do is sample using this sample button here the assembly object, and let's change the title to be, let's call it assembly time. Okay, reset, run the model, speed it up a little bit. We see our 4 different part types. And is our dashboard chart working? Yes, it's saying the average state time is 39.84 seconds. The max state time is that. and state time is the assembly time. Okay, stop the model, reset, and let's move on. Model 1 Phase 5 will introduce the experimenter, groups, the dispatcher, and the scenario chart. We're going to develop an experiment to compare the model outputs if the number of processing stations ranges between 1 and 3 versus the number of available operators also ranging from 1 to 3. As outputs, we want to look at the throughput rate of the system and how it changes with additional operators and processors. An advanced application is to test the rework rate. What if the rework rate drops from 20% to 10%, so making the rework rate be a variable. This is the layout, the same as we had in Phase 4 with one change. We're going to use a dispatcher that's connected to the operator, allowing us to try more than one operator. Okay, let's first talk about object groups. Grouping creates a means to collectively refer to multiple objects. Create a group, use the name of that group to collectively refer to all members of the group. It helps with organization and structure of the model. It works with the experimenter to automatically create or remove new objects as needed, and we're going to take advantage of this in this phase of the model. Grouping also makes charts based on multiple objects much easier to make. Okay, the dispatcher object. It coordinates a team of task executor objects, like operators, that need to share a common queue of tasks. So it receives the tasks, queues them up, dispatches them out to different members of the group based on different criteria. It uses port connections to communicate with the objects, creating the task and the members of its team. So as shown in this image here, this is the dispatcher, and it has 3 output port connections to each of 3 separate operators. So the dispatcher dispatches the tasks out through its output ports. Center ports are typically used as connections to those objects that are requesting the task executors, and we've seen that already, but our center ports were connected directly to the operators. Now we're going to connect them up to the dispatcher, send our request to the dispatcher, and let the dispatcher decide who gets the task. It uses a pass to field, and the logic of that field is similar to the send to port field for processors. This is the field on a dispatcher that's used to pick an available team member. The number of task executors attached to a dispatcher is a variable the experiment knows how to change. So that's going to come in handy for this phase of the model. Okay, what does an experimenter do? Well, it executes multiple replications of your model in parallel. 1 replication per processing core. If you have an 8-core machine, it'll execute 8 replications in parallel. And each replication, which will be a run of the simulation model for a length of time, will then report back its results at the end of its run. It also allows a model to be run with different inputs of variables like number of objects, or change the cycle time duration or something like that in the experiment. We call those scenarios. It automatically creates aggregated output reports. So, definitions. Replication is a single run of a model. A scenario is a set of variables that will be changed in the model for a group of replications. The user defines what values will be assigned to the variables for each scenario. You'll do that in table form, as you'll see in a minute. There's a warm-up time you can define for an experiment. This is the simulation time when the statistics of a replication will be reset. It helps collect data for steady-state operation only, so you can exclude from your statistics the ramp-up time when the model's coming up to speed. And then you define an end time. This is the simulation time when one replication will end and the next one then will start. Experiment variables. You may use a predefined variable from the drop-down list of options, or design your own, which is a more advanced way of doing it. The experimenter can only change numeric or text inputs. For more advanced variables, it may be necessary to create labels or input tables whose values can be changed by the experimenter and have that data read by the model. Some knowledge of design of experiments can help reduce the number of scenarios needed to obtain useful information so that you don't have to run every single permutation of all your scenarios. Let's now talk about what it takes to have a successful analysis of your model. Broken it out into 9 steps here. The first is to examine a single run of your model before going into an experiment. Check for extremes, omissions, outliers, unexpected results, etc. You do this by watching the animation first and then by plotting some time plots like this one here, a content versus time, and it can help identify problems like, can you explain this flat line? Does it make sense to you? Why the content held constant at 2 for a while? And things like that. Number 2, choose a performance measure that you feel is reflective of your model's purpose or focus. Oftentimes you can boil it down to a single performance measure, at least for the initial evaluation phase. Then create a new chart on your dashboard that will report the selected performance measure. Add an experimenter to your model. This is in the statistics menu. And create, for starters, just a single scenario. And it'll include the decision variables that contribute to your performance measure. On the Performance Measure tab of the Simulation Experiment Control window, choose what charts you have already set up in your model will act as the experiment's outputs. So you'll see when you click the plus button a list of charts you've already made in the model. Go down to those charts and then you can, in pop-up menus, choose whether or not you want the average, the sum, the min, and the max for the particular PFM or performance measure. You can have as many performance measures identified as you want. Then click the Experiment Run tab. Specify the number of replications, typically around 30 replications will work for you. Check the Save Statistics Data box right here and verify the end time and run time are what you want. And if you need a warm-up time, identify that as well. After all that is set up, click the Run Experiment button. You can now, after your experiment has finished, view the results using this View Results button on the experimenter. You can define additional scenarios at this point to evaluate the impact of your decision variables. So, going back to the Scenarios tab, use this plus button right here to add more scenarios. They'll be called Scenario 1, Scenario 2, Scenario 3 until you rename them by double-clicking on the header of that column, or in other words, scenario. And then identify the values for each of your variables that you want to apply for that scenario. You can also create a new dashboard window and add the scenario chart and point it to any charts you have made. So the scenario chart is going to give you information in addition to the PFM or performance measures you were able to view with the View Results button we mentioned earlier. So in this example, in this scenario chart, it was pointing to the operator state pie chart. And then it's showing you a pie chart for each one of your scenarios that you defined for your experiment. Okay, it's now time for you to try to build this model on your own. Okay, I will now demonstrate how to complete Phase 5 of Model 1. First of all, let's add a dispatcher. I'm going to disconnect the center port connections that go from this operator to the queue and the processor, and instead make center port connections from those two objects to the dispatcher. So to disconnect center ports, it's the W key. You hold down on your keyboard and click and drag and click and drag. Now make center port connections with the S key. Click and drag, click and drag. Now the operator needs to be connected to the dispatcher with a regular output port to input port, so that is an A key. Click and drag. So now the queue and the processor will send their request to the dispatcher and let the dispatcher send out a request to however many members of the team are connected to its output ports. And the experimenter is going to vary the number of operators. Okay, now let's create some groups. By creating a group on this processor here, by right-clicking and saying Object Groups, add a new group, by doing this, we're going to be able to set up a variable in our experimenter that will vary the number of processors in the group. And it'll go ahead and add the new processor, make all the connections that are on the current processor. Works really slick. For the dispatcher, there's a variable in the experimenter that you can specify how many members a dispatcher team will have. And so we can do it that way, but we're still going to create a group of operators and a group of processors. And the purpose of the group of operators is not to be able to vary the number of operators, but it is in order to get dashboards with results that are for all the operators. Okay, so we'll call this processor group. And for the operator, right click on it and say add a new group, and we'll call this the operator group. Okay, now let's open our experimenter. It's in the statistics menu. Experimenter opens up this simulation experiment control window. I'm going to add a couple variables. I meant to click the arrow here. There we go. Number of objects in a group. Processor group. It'll have a list of all the groups in our model. I want to say the processor group. And we'll call it variable 1. And delete this one. Okay. Now add another variable by clicking on the arrow. Say number of task executors. This is the one we want to use. It's set up to where you can choose a team, it calls it here, which in the drop down will have a list of all the dispatchers in your model. That's what it'll use to represent the team. And it's variable 2. Okay, now we're going to add as many scenarios as we need. Let's start with 3 scenarios, and scenario 1 will be where we have 1 processor and 1 operator, and then 2 and 2 and 3 and 3. But you can make a combination of any combination you want, and that would require what, 9 scenarios to capture them all. Okay, let's close that. Now I've kind of ran out of room on this dashboard, so let's open up another dashboard. Add a dashboard. There we go. And we want to get state charts. State pie chart. This pie chart will be the processor group. And then you'll see after we choose the group, it knows what kind of objects are in that group and then shows us all the states associated with that object type. Go to the text here and come up with a custom title, and it'll be a state pie chart for the processors. So let's call it processors state pie chart. Okay, now let's add another state pie chart, and for this one we're going to choose the operator group. This is why we set up the operator group, was to be able to choose it here in the dashboard state pie chart. We did not use it in the experiment variable like we did for processors. Just wanted to make that clear. Okay, and we'll call it operators state pie chart. Okay, let's run the model. Make sure it runs and we get a dashboard displayed. We do. Although I spelled operators wrong, and that's going to bug me, so I'm going to go change that. Okay, looks like they're both working. And our baseline model has one processor and one operator. Now let's reopen the experiment window. And let's run for what? 3 days or so. No warm up. And replications per scenario, we'll go with 30. Want to check this box to save statistics data for each replication and run the experiment. Allow access to all the cores, and there it goes. So I have an 8-core machine, so you should see 8 replications in progress at any given time running in parallel. So we're working our way through 30 replications of scenario 1 right now. Okay, the experiment has successfully completed. Go ahead and close this, and you won't see anything on these charts here. If we create a chart called a scenario chart, this is how we get data displayed from an experiment. It's called a scenario chart. And you choose regular charts that you have already created in your model. You choose them here. Here's the state, is the chart type, and then it's showing me the title here. So I want that one, and then I have the ability to choose which scenarios I compare on that chart. Apply that. So there's our 3 different scenarios. Okay, let's create another chart. Need more room. Well, let's just make this bigger here and add another scenario chart. Let's see, it's in general here. And this one will be for the operators. So I should name, let me choose the 3 scenarios. Should name it the operator states. Click back on this one and change its title to processor states. So what does it show? Well, let's look at the processor states. So scenario 1 just had one processor in it, and here's the pie chart for it. So that processor was busy 43% of the time. In scenario 2, we had 2 processors, so we got 2 pie charts, and they were in the 23% range, both of them. This is utilized. What it's doing is combining the states of processing and setup to come up with a utilization of 43%. And so this is utilized about 23% of the time, the two processors in scenario 2. And then we have 3 pie charts, one for each of the 3 processors in scenario 3. And the utilization averages, what, about 15% or so. And then operator states are similar, but a little higher than the processors, because the operators have to walk around and do more. Okay, that finishes out Model 1.